So the last talk for today is Chinburg, and we'll talk about transitions invariance with Artin maps.
I should also say that Kai is going to give a talk after me. I'm not the lesson. I just want to say that when I first heard about Mignon's ideas, I think it was Rosette, I thought this was incredibly exciting. The idea that you could combine number theory physics potentially revolutionary. So, unfortunately, my physical intuition is absent, so I'm mainly going to be talking about number theory. But one reason I like studying Mignon's ideas is it presents lots of challenges for people who think about étale, cohomology, and duality pairings. So I want to describe some work that this group of people have done in trying to compute some of Mignon's invariants and relate them to rather classical number theoretic things like Artin maps. So let me describe what these examples are. So here's the outline. I'm going to recall the definition of the invariant, which we've seen multiple times. Then I'll talk about eventually a formula for it using Artin maps in the case of unramified cyclic extensions of number fields. It would be interesting to know what the topological version of this formula would be. I want to say some things that you can prove with the formula. And one thing that we're actively working on these days is to try to understand Mignon's invariant from the point of view of natural pairings in étale cohomology, which Mignon talked about from pairings before. There's another pairing that goes back at least 15 years by McCallum and Sharifi. The McCallum-Sharifi pairing, I'll define that later, but it's turned out to be the inspiration for a lot of important things in Iwasawa theory. Sharifi's conjectures, for example, which are basically taking the Mazer-Wiles proof of the main conjecture and seeing how much more of those techniques actually could show about Iwasawa. So we're pretty actively involved in trying to understand the connection between the pairings that are related to Mignon's work and McCallum-Sharifi. And I'll make this little suggestion about what might work. So let me recall Mignon's invariant. You take an abstract conjugate of G. We're going to take a totally complex number field with a primitive nth root of unity in it. He takes a class in H3 of G with coefficients in UN, where G acts privily in UN. And you look at the spectrum of the ring of integers of F. You take some homomorphism from the étale fundamental group. Most of the time, I'll think of that as a surjection, which would then be giving me an unramified G extension of F. Starting with this class in H3, we can pull it back to a class in H3 of the étale fundamental group. And via check étale cohomology, we get a class in H3 of the spectrum of the integers with coefficients of UN. And the Chern-Simons invariant that Mignon defined is simply that class when you use the fact that H3 of spec OF with UN is canonically isomorphic to Z mod. This is like the fundamental class isomorphism, cupping with the fundamental class in H lower 3 of a 3 manifold gives you this isomorphism.
Can you say again what eta x is?
Oh, it's simply the generic point. So this is an artifact of the yoga about étale fundamental groups. It simply means you need to pick some algebraically closed field that contains the fraction field of F. And the étale fundamental group, in principle, depends on looking at all of the everywhere unramified extensions of your field within that algebraically closed field. Algebraic closures are not unique. They're only unique up to isomorphism. So you need to pick them, and then you can define this étale fundamental based on that choice. I want to make one little suggestion here. Mignon started with a class in H3 of G with coefficients in UN. So Oh, something happened. I want to make a comment. Well, H3 of G with coefficients of mu n is just X3 of the integral group of Z with mu n. But you could start with a class in X3 of Z mod n with coefficients of mu n, which is a perfectly reasonable thing to do. And then when you do that, you end up with classes in X3 over X of Z mod n with mu n. Okay, now that looks like a sort of dumb idea, but this actually seems to have something to do with McCallum and Sharifi's work. That if you soup up the invariant to lie inside here, you get something in a bigger group, because if you think about computing the long exact X sequence associated with this sequence in the first variable, you're going to end up with short exact sequences like this. Just because this is multiplication by n. And the multiplication by n map is going to kill groups that were killed by n. So the long exact X sequence associated with this sequence, in fact, gives you split exact sequences. So for example, when I equals 3, Mignon's invariants are in an H3, which is a Z mod n, but there should also be things that are coming in H2. And those invariants are related to McCallum-Sharifi. So I think ultimately this is the way to interleave McCallum-Sharifi with Mignon's work. Yeah?
So for a complete outsider, I don't know much of the story. Why degree 3 special?
It's somehow because the spectrum of the ring of integers is like a three-dimensional manifold. It's a tall cohomological dimension is 3. Above dimension 3, it's 0. And there's this fundamental duality pairing, duality theorem, that relates in ith cohomology of a constructible sheaf to x to the 3 minus I of the sheaf of G. So the Poincare duality looks like it's dimension 3. So I'm going to come back to this at the very end. I promised Henrik that I would make some interesting mistakes. So the interesting mistakes will be at the end of the talk. Well, maybe before. Now, one of the inspirations for this talk is this great result by a group of 5 authors listed there, that there are infinitely many examples where the group that's involved in the invariant is one of Z mod 2, Z mod 2 plus Z mod 2, S4. And in those examples, you can find infinitely many where you get a trivial Chern-Simons invariant and infinitely many. And their method, well, this is an adequate summary of their method, but Mignon described a formula in his first talk here. You can see it as comparing local and global trivializations of 3 cocycles. So we got involved in trying to, we were trying to compute this invariant, but we made some mistakes for a while, but eventually we sorted out how to compute this in terms of arc maps. And that's what I'm going to describe. Now the main outcome, one of the outcomes is this, that you can show there's infinitely many totally complex fields, so that when you take C to be a generator for G is a cyclic group order n, you take C to be a generator of H3, of the group of coefficients in UN. You can, over this F, you can find an F for which this is non-trivial, and you can also find another F for which it's trivial. So the Chern-Simons invariant really depends on the unramified cyclic Kummer extension that you're picking. In both of those terms. So let me talk about Artin maps. So for the number theorists, this is very familiar, but by the way, I want to just identify Z mod n with mu n sometimes when I don't want to care about the difference. So I'm going to fix an isomorphism. And I'm going to suppose that this surjection from the Étale fundamental group to G is surjected. So what's then happening is that we're going to have a fixed, unramified G extension, where the group is now getting identified canonically with Z mod n. Fix some identification. Now the Artin map is a map from the ideal class group of the base to this Gauss group. And the way that it works is that for every prime ideal of the base, if you take the prime of the ring of integers and you look at a prime over it, the subgroup of the Gauss group that fixes this prime is the decomposition group. It's cyclic and generated by an element that raises elements in the residue field of Q to the power given by the order of the residue field of Q. So that's the Frobenius automorphism of P. And the Artin theorem says that this map from ideals factors through the ideal class group and gives you a surjection onto the Gauss. So there's lots of interesting ways to calculate Artin maps, and that's what we want to use. So now let's come back to the situation where I've now picked this unramified cyclic Gauss group extension with group Z mod n. And the question is, if I want to construct for some class in H3 of G mu n that's a generator, I'm trying to compute the Chern-Simons invariant of F and C, where F is associated to this extension and this isomorphism. Okay. So now in the multiplicative group of K, G is acting in the multiplicative group. Now the multiplicative group sits in an exact sequence like this, where the middle map is simply raising to the nth power. Now if you think about that four-term sequence, you can split it into two exact sequences, right? So I can imagine putting a term here, splitting into two exact sequences. Then when you take the G cohomology of those two sequences, each of them has a boundary map. So the first boundary map goes from the G invariance of this quotient to the H1 of the kernel of the map from here to here. But then I identify that kernel with the co-kernel of the map from here to here. Then there's another boundary map that gets me up to H2. So that's what this is. This is the double boundary map associated with a four-term sequence. And what you can prove with a bit of Gauss cohomology is that you get this exact sequence where this group is cyclic of order n. So to calculate Mignon's invariant, it's enough to know a class, enough to know an element of K that defines some coset whose image is a generator. One of the problems then is how would you ever find such a thing? I'm going to talk about how to find a gamma. But once you find an element of K star, this extension, which lives in a G invariant coset and generates the H2, then you can calculate Mignon's invariant this way. H1 is just the homomorphisms from G to Z mod n. But remember, G I've identified with Z mod n, so there's an identity map. I'm always going to take C1 to be the identity map. And C2 then is a class in H2. So we can take a cut product of a class in H1 and H2, get this class in H3 that's actually a generator. And then if you want to calculate the Chern-Simons invariant of that class in H3, you can do the following. You look at this gamma, take its norm down to F. That has to be the nth power of a fractional ideal of F. And then you can look at the image of that under the Artin map. So there's a bunch of identifications happening here, namely the Artin map maps to the Gauss group of K over F, and I've identified that Gauss group with Z mod n, so it makes sense to talk about the value of the Artin map as an element of Z mod n. Okay. So, I mean, one question is, what's the topological version of this? I mean, there should be some topological formula. That'd be interesting. I'm not going to talk a lot about proofs, but I will if there's interest. It's actually a difficult exercise, at least most for us.
Well, I have one answer to the question about the topological version, so we can do this after the.
Okay, great. Now I want to talk about how to construct this gamma, because in the theorem, well, it's all well and good to say there is a gamma, but The question is, how would you construct it, and because that's the crucial thing if you want to compute this invariant. There's two ways to do it. One of them using some classical theorems of Hilbert, and another one using cyclic extensions of degree n squared. So if you have an unramified extension of cyclic degree n, and you look at an nth root of unity in the base, that's a local unit everywhere. Right? But in an unramified extension, all the local units are in fact norms, locally. So the nth root of unity is because it's a local unit everywhere, it's everywhere a local norm. But Hilbert's norm theorem says that in a cyclic extension, if something is a local norm everywhere, it's a global norm. So then the Zn is a norm of something. But now, if you take that x and raise it to the nth power, it becomes something of norm 1. So since the norm of this is 1, Hilbert's theorem 90 says that if I take a generator, that I'm going to take the generator identified with 1, x to the n is sigma gamma minus over gamma. And that's the gamma we want. That gamma will work. So this gamma defines an invariant coset under the action of the group. And when you go through the construction, you can compute the Chern-Simons invariants of that. So that's useful, but again, you have to produce some special elements, namely an x, and then you have to solve 90 and norm. So again, that's a bit of a problem. But there's another way to go at finding gamma. So this is an interesting theorem, and it's related to this Bachstein phenomena that Mignon was talking about. That if you take any unramified cyclic extension of a field that contains an nth root of unity, you can show that this lives inside some cyclic extension of degree n squared, which may ramify. And furthermore, that extension is unique up to twisted. So what that really means is if I write this down as the Kummer extension associated to some element of k, well, I could adjust this gamma here by an element of f and end up with another cyclic degree n squared extension, which would contain k, because, yeah. But this is any cyclic degree n squared extension that contains k has to be just a twist like that. So now, what you can use this for is to just say that this gamma will work. I mean, that gamma is going to be the type of element that we wanted to generate a G invariant coset. So if you take the norm of gamma and write it as, the theorem says that that's an nth power of some fractional ideal. If you can factor this ideal into a harmless part, the J prime, those are all ideals that are either split up to k or not ramified in L over k. Those will not affect the value of the Artin map. So it's enough to look at the other ideals, the other fraction, the other ideals. So if you can factor the idea that way, then you have control over what the value of the Chern-Simons invariant is. The reason that this is kind of useful is that you can construct now extensions with Chern-Simons invariant by studying cyclic degree n squared extensions. And we have different ways of constructing lots of those that have good properties. So let me talk about that a little bit. Now this is a mild extension, slight extension of something Mignon said. If this were unramified, then in that last slide, we could take I prime to be the identity. So in general, you can do something a little more. If every prime of f that ramifies here actually already has to split up to k, then the Chern-Simons function is 0. And the other thing that you can do is if you can arrange for there to be exactly one prime of f that is undecomposed. So there's a unique prime over it now, but I want this prime to be ramification degree exactly n. So if the inertia group if there's only one prime that ramifies, and the inertia group of the prime over it has order n, this one's n here, then that says that P is inert up to this point, and then it's totally ramified. So an inert prime will have Frobenius that's a generator of the Galois. And so in that theorem, the only prime that's going to come up is this P, and its Frobenius generates the Galois. So what will happen then is the Chern-Simons invariant will have order n. So now if you want to construct lots of extensions with non-trivial Chern-Simons invariants, you simply need to construct lots of unramified extensions of cyclic degree n over f, which have a cyclic degree n squared extension in which there's only one prime that ramifies. And that one, prime over it, should have inertia group over n. Now the natural way to try to go about doing that is to simply start with some cyclic degree n squared extension, and then make some base change to absorb all the ramification that you don't want. The only thing you have to worry about is that in making a base change, you may end up with lots of primes that ramify. If you absorb ramification that you don't want, the prime where you do want some ramification might split. So you want to prevent that from happening. If you work with that long enough, then you can produce lots of fields F over which there's two cyclic unramified extensions. And one of them looks like this one and has a non-trivial Chern-Simons invariant, and the other one is totally unramified. So that's a little more delicate than it looks, because if you try to do it with a naive base change argument, you run into the problem that you may end up with too many primes that are ramified in the one cyclic degree n squared. Okay, so now Ralph Greenberg was one of our group, so he started looking at the classical cyclotomic case. For example, if you take a properly irregular prime, what does that mean? It divides the class number of z zeta n, but it doesn't divide the class number here. As far as we know, Vanderveer says this has never divided. If you take any cyclic unramified extension of this, then the Chern-Simons invariant turns out to be 0. And this is kind of interesting. Let me erase the board a little bit. Is there an eraser?
But there's one over there. Yeah.
Okay, here. Let me say a little bit about how that works. It's a nice argument. So remember, n is prime. And what you end up doing is saying that if you take any cyclic unramified extension, in fact, you can fit this into, as long as this is n doesn't divide the class number down here, it's an interesting fact that any cyclic degree n extension of q zeta n will land inside of an extension that the Galois group is Zn, the Nn compass. So you can embed every cyclic degree n extension into a Zn extension. Now, once you know that's true, then there is going to be a field L here, which will have Galois group Z mod n squared. That's the type of extension we need to compute this invariant. But now, the only prime that ramifies in this Zn extension is the unique prime over n here. But that prime is, in fact, generated by 1 minus zeta n. And 1 minus zeta n is a principal ideal. So if you look at the Frobenius of 1 minus zeta n, the unique prime over n in this field, it's principal. So it splits in an unramified extension. So you're in the situation where you have a prime that has to remain undecomposed all the way up, but it's split, this prime will split to this field, splits to this field. That's all we need. Because once it splits to this field, then it's the only prime that ramifies, and it's Frobenius in the Galois group of K over Zn will be triggered. So the formula tells you what the transition there is. And you can do some other things with cyclotomic theory. Well, at least for Abelian extensions of Q, you can prove it. If you have any, there's various other cases where you can prove that the transition vanishes. Let's see. Go back here. So I think I'm not going to say more about this. I do want to talk about these two pairings because, you know, Mignon's invariant is a beautiful thing. What's behind it is a pairing. And in some sense, the pairing contains much more information. So trying to understand different pairings in Galois and étale cohomology seems to be the main point. So I want to talk about two different ones. So the first one is the McCallum-Sharifi pairing. Let me indicate how this works. So I take a finite set of places of F that contains the places over M. I look at the S-class group where I take the ideal class group and I invert the classes of primes that are associated with places in S. Now, I'm actually going to do a slight special case of what they do. They do something a little more general. But we can look at the subgroup of F so that when you join an nth root of an element in the subgroup of the multiplicative group, you get an unramified extension. That's exactly the kind of element that we want to produce these cyclic unramified Kummer extensions. And there's a pairing they define between this subgroup and the unit group. And the value of the pairing is in the quotient of the S-class group mod n tensored with mu n over z. Now, where does this come from? It's really this, that we're going to be looking at elements of this mod nth powers of the multiplicative group of F. And similarly, I'm going to be looking at units mod nth powers. Now, each of those groups, this n should have been a 1. Sorry about that. That should have been a 1. If you look at F star mod F star to the n, you just get the H1. Well, really, of the Galois group of F bar over F with values in F bar star. What do I want to say? Let's get this